This work builds on the previous introductory descriptions of models of the structure of matter using the toroidal element. In this work, we will show models of carbon, nitrogen and oxygen atoms and some of their homonuclear bonds. As mentioned in previous works, the structure of the atomic electron shell depends on the structure of the atomic nucleus. Nucleons in an atomic nucleus built according to the model of the ring theory have their experimentally proven magnetic moment. The rotations of the charges are bound to neighboring nucleons by means of magnetic field components and thus form deterministically and explicitly defined bonds. The planes of these globules are perpendicular to each other in the carbon atom. One of the most important elements of the structure of the nucleus model is the distribution and orientation of the magnetic moments of the proton rings in the adjacent globules. In one globule, the magnetic moment vectors of the protons point inwards, and in the other globule, the vectors of magnetic moments of the protons point outwards from the globule. This structure of the nucleus globules affects the orientation of the magnetic moments of the electrons, which are bound to the individual protons of the nucleus. Electrons always have an anti-parallel direction of the vectors of their magnetic moments with respect to the magnetic moment vectors of the control protons. Therefore, each of the bonding electrons have both 2p and 2s with respect to the nucleus of the atom in the opposite direction of the magnetic moment vector. Such an arrangement of electrons allows carbon atoms to form different kinds of bonds with other atoms. To properly understand bonds, it should be emphasized that the electron has only one type of magnetic moment, unlike mathematically defined spins. Its dual form is determined only by its orientation towards the nucleus of the atom. If we move an electron from the upper globule to the lower globule, its properties do not change at all. Only the direction of its magnetic moment vector with respect to the nucleus of the atom changes from the out type to the in type. It always has an anti-parallel direction to the magnetic moment vectors of its controlling protons. In the pictures we can see different views of the schematic representation of the carbon atom models. Model of the carbon atom according to the ring theory in spatial mapping. The homonuclear bonds between atoms are realized by covalent bonding. We can recall that it is a force bond between ring electrons bound by a magnetic field that have parallel vectors of their magnetic moments. The covalent bond is based on the equilibrium of electrostatic and magnetic repulsive forces between protons and electrons. To form a covalent bond, the atoms must be rotated relative to each other so that the magnetic moment vector of the proton of one atomic nucleus is directed outward from the nucleus of the atom, and in the case of the other atom, the magnetic moment vector of the proton is directed inward of the globule of the nucleus of the atom. The magnetic moment vector of an electron always has an anti-parallel direction against the magnetic moment vector of the proton to which it is bound in the atom. For a covalent bond to be formed between two electrons, both electrons must have a parallel direction of their magnetic moment vectors. Akaska modelu jednaduše vazby mezi atomy uhlíku versus molekule ethanu. The double bond between carbon atoms is formed by a sigma-type bond consisting of two electrons s2, and a second p-type bond consisting of two electrons p2. Carbon atoms are rotated to allow bonding electrons to form covalent bonds with parallel vectors of their magnetic moments. An example of a model of a double bond between carbon atoms in an ethylene molecule. The distance between carbon atoms is less than that of an ethane molecule. The triple bond between carbon atoms is formed by a sigma-type bond consisting of 2 electrons s2, and 2 pi-type bonds consisting of 2 p2 electrons. Carbon atoms are rotated to allow bonding electrons to form covalent bonds with parallel vectors of their magnetic moments. An example of a model of a triple bond between carbon atoms in an ethene molecule. The distance between the carbon atoms is less than that of the ethylene molecule. The model of the nucleus of a nitrogen atom according to the ring theory consists of 2 globules. One globule has 2 bonding electrons attached through protons, and 3 bonding electrons are bonded to the other globule via protons. In one globule, the magnetic moment vectors of the protons point outwards from the globule, and in the other globule, the vectors of magnetic moments of the protons point inwards from the globule. In the nitrogen atom model, 2 protons of one globule are bound to one type 2s electron and 1 electron of type 2p with magnetic moment vectors pointing from the nucleus of the atom outwards. Normally, homonuclear bonds occur in nitrogen. Due to the high variety of binding situations, nitrogen occurs in virtually all of its oxidation states, -3 to +5. Example of a model of a nitrogen atom. Demonstration of a model of a simple bond between nitrogen atoms in a hydrazine molecule. Model of triple bond between nitrogen atoms in a nitrogen molecule. This triple bond is very strong, resulting in a low reactivity of the nitrogen molecule. The model of the nucleus of an oxygen atom according to the ring theory consists of 2 globules. 2 bonding electrons are bonded to one globule through protons, and 4 bonding electrons are bonded to the other globule through protons. In one globule, the magnetic moment vectors of the protons point outwards from the globule, and in the other globule, the vectors of magnetic moments of the protons point inwards from the globule. An example of a model of an oxygen atom with its vectors of magnetic moments of bonding electrons. An example of a model of a simple bond between oxygen atoms in a hydrogen peroxide molecule. Using a model of an oxygen molecule, we will show the significance of magnetic moments of protons in the nucleus of an atom. We know from experiments that the oxygen molecule has 0 dipole moment and is one of the few molecules that exhibits magnetic moment. Since the molecule is bound by a double bond, we can certainly think of the simplest solution of bonding between 2 2p electrons bound to one globule and 2p electrons bound to the same globule of the other atom. But such a union of atoms does not allow for the formation of a covalent bond between electrons with parallel magnetic moments, and the molecule would not show any magnetic moment. The same problem occurs with the union of electrons in globules with 4 bonding electrons. If we were to combine electrons with magnetic moments pointing towards the nucleus of an atom with electrons whose magnetic moments point outward from the nucleus of the atom lined up one after the other, such a bond could be formed, but the molecule would show a dipole moment. Both conditions of the experiments are met only by the connection of atoms rotated by 180 degrees and placed next to each other. Such an oxygen molecule exhibits a magnetic moment, and its dipole moment is 0. Model of the double bond of an oxygen molecule. Model of double bond of carbon dioxide molecule. The following table shows that using the ring structure of the elementary particle model, the structure of the nucleus of atoms and the models of molecules according to the ring theory, it is possible, using the basic laws and properties of electromagnetic fields, deterministically and with a relatively simple mathematical apparatus to determine the radii of atoms and their ionization energy, the distance of atoms in a single covalent homonuclear bond and their binding energy. More information about ring theory at www.ringtheory.eu. Thank you for your attention and keep an open mind.